Welcome to Mastering Solutions. We'll start this question by using the magnification equation, which we know is magnification is equal to the image height over the object height. And it's also equal to the image distance over the object distance, which is negative. So we're going to use this, the magnification, and set it equal to the distances. So when we rewrite that, magnification is equal to the negative image distance over the object distance. And the question tells us that we want magnification to be 2. We're trying to solve for the image distance here. We're going to use that in the next step. So first, let's isolate this by multiplying both sides by negative s. And so now the image distance is equal to the negative m times s. So now the question tells us that we want the magnification to be 2, and the distance from the teeth is 1.2 centimeters. So we have s prime is equal to a negative 2 times the 1.2. Let's put that in standard units. You could leave it in the centimeters if you want for this step. It doesn't really matter. For the next step, we do definitely want it in meters though, so we might as well just do it now. We can either change this to 1.2 times 10 to the negative 2, or for this one, it is pretty simple for this question to just move the decimal place 2. So now we have negative 2 times 0.12, negative 2 times 0.012 gives us negative 0.024, so negative 0.024 meters, which is also 2.4 centimeters. So this is the location of where the image is going to form for this mirror. Since we want it to be an erect image, what this negative tells us is it's going to be a virtual image. And so with mirrors, we can assume that this is likely going to be a concave or a converging mirror, because with a converging mirror, to have a virtual image, we want it to be up here on the opposite side of the mirror with the negative, and the image is likely going to be inside of the focal point. So now what we'll do is the next step, we're going to use the thin lens equation. We're trying to figure out what the focal length is. They want us to use ray tracing to estimate the focal length, but we're just going to calculate it because we're not going to be as precise on our drawing. So 1 over the focal length is 1 over the image distance plus 1 over the object distance. And now we have both of these solved. So now we can plug this in, and that's equal to 1 over the image distance, which we found is a negative 0.024 meters. And then we're going to add the object distance, which is a positive 0.012 meters. There are a couple different sign conventions for mirrors and for lenses as far as when is something positive and when is something negative. In our book, what they use is the convention that if it's on the opposite side over here, so in other words, a virtual image, we're going to have a negative value. If it's on the same side as the object, it's going to be a positive value. So with lenses, we would think of it if it's upstream, it's positive for an object. If it's downstream, it's negative. And then if an image is downstream, it's positive. And if it's upstream, it's negative. That may be confusing, but for a mirror, just think that if it's on the same side, it's positive. If it's virtual and over here, it will be negative. So in a converging mirror, for our sign convention, the way we're using it, the focal length for a concave mirror will always be a positive value. So when we plug this in here, we have 1 divided by a negative 0.024, and then we're going to add to that 1 divided by 0.012 for the object distance. So that gives us 41.67 diopters. And we want this in the focal length, so we'll take the inverse of that, which gives us 0.024 meters or 2.4 centimeters. So this is the focal length for this mirror, 2.4 centimeters, and the image forms at a negative 2.4 centimeters. Now the question, as far as how can we tell if this is a converging mirror, what they want us to do is they want us to pretty accurately draw the picture here. So we know that we have the object distance at 1.2 centimeters, so we'll say right there. And we know that we want this other one to be twice as big and it's twice as far, right? So this is 1.2 centimeters. This needs to be 2.4 centimeters and about like that. And so if we were to have a mirror, how do we get the light rays to converge over here? If we don't know, obviously starting the question, we're assuming, like we talked about, it's concave, but if we didn't know what kind of mirror this is, we would start off doing parallel light, and then that would go through the focal point. And if it was a concave mirror, it would focus like this, and then we would extrapolate it back like that. And then we would have one through the center of the lens, and then the incidence angle and the reflection angle would be the same, and it would go like that. And then we would have through the focal point, we would come as if from the focal point, and then it would come up and then reflect out parallel. And so it would come parallel. So obviously this is the only way that we can get this kind of image here with a mirror. So we know that it has to be a converging mirror. If we were to have a diverging mirror, what would happen is if we had it here and we drew parallel and then through the focal point, it would diverge out like this because the focal point would be back here. We would have one straight through the center of the mirror. And so it would come out like that. And then we would have straight through the focal point, and then it would come out parallel like this. So this is the ray tracing for a diverging mirror, but we get a minified image. And so since we want a magnified image and we want it erect, we know that it has to be a concave mirror inside the focal point. So hopefully that made sense. I worry that that was a little confusing the way I went through that quickly, but we know that we need a concave mirror. The image is going to form a virtual erect image 2.4 centimeters behind the mirror. And then the focal point, they wanted us to estimate the focal point, but we calculated it to be 2.4 centimeters.